Our final set of videos is going to deal with the concept of angular momentum and, more importantly, the law of conservation of angular momentum. If you recall, when we did linear momentum, we had a formula that said momentum could be calculated by taking the mass of an object and multiplying by its linear velocity. Please note on your AP formula sheet, there are two formulas that use the letter P. Lowercase p is momentum and is mass times velocity, but we also had uppercase p for power, which was energy divided by time and was a completely separate concept. So please don't confuse those on the AP test. But back to this. Knowing that linear momentum equals mass times velocity, we can also talk about an equivalent idea in the world of rotation, angular momentum. And just as it made no sense to use the letter P to represent momentum, we are going to use the letter L to represent angular momentum, in this case, a capital L. And similar to what we've been doing before, instead of just looking at the mass of the object, we are going to look at I, the rotational inertia of the object. And instead of multiplying by linear velocity, we are going to multiply by omega, the angular velocity of the object, giving us the formula L equals I times omega. Now, it is possible to translate linear momentum into angular momentum, which we will do in a later example. But you need to remember that there is a formula that I told you in rotational kinematics notes was important. That linear velocity can be converted into angular velocity by doing v equals omega multiplied by r, how far away the point is from the axis of rotation. And recall that this formula works because linear velocity for something moving along a circular pathway can be found by taking the circumference and dividing by the period, which will be 2 pi r divided by the period. But finding angular velocity means taking how much angle you rotate in one complete circle, 2 pi radians, and dividing by the period. Therefore, if we take 2 pi radians, divide by the period, and then multiply by the radius, we get the same formula for the linear velocity. This formula is not on your AP formula sheet, and since you get to make your own this year, I strongly encourage you to add that to your arsenal. Just as in the world of linear momentum, where I told you that the actual momentum of an object is not nearly as important as the law of conservation of momentum, we have the same idea in the world of angular momentum. So the law of conservation of linear momentum simply said that you add up all the individual momentums in a system before some sort of interaction, and that total momentum should be equal to the sum of all the momentums of the objects in a system after the interaction. Often this is going to be a collision. Sometimes it's going to be objects exploding off of each other. And this will be true unless there is some force from outside the defined system that is changing the total momentum of the system. But if there are no outside forces, the linear momentum must be conserved. The same is true with angular momentum. The sum of the angular momentums of the objects in the system before any interactions or changes will equal the sum of the angular momentums of the objects in the system after any interactions or changes. This will remain true unless there is a torque from outside the defined system acting on the system. So instead of looking at forces this time, we'll, as typically done in rotation, look at torques instead. Next, I'm going to go through two common angular momentum problem situations, but I'm going to do that in a different video. This is not included in the first set of notes that you need, but if you go to the Schoology page, there will be 2 more extra pages going through these example problems. See you in the next